Welcome back everyone. Today's video is an explanation of problem F from the AtCoder Beginner Contest 308. I have provided the correct Python code in the video description, so please check it out after listening to my explanation. Let's begin with the problem statement. We have n items and m coupons. The prices are given in array P. The ICE coupon can be applied to an item whose price is at least Li, and it provides a Di discount. Multiple coupons cannot be used for the same item. Our problem is to find the minimum total amount of money required to buy all n items. In the example, if we use the coupons as shown in the right diagram, the expenses can be calculated as follows. However, there might be a more efficient way to buy all the items, so this is not the final answer. Let's proceed to solve the problem. Our initial approach is to test all possible ways of buying the items. The number of possibilities is about n permutate m, which is impossible to calculate. We need to use a more efficient algorithm. The problem involves making pairs between items and coupons, making it a matching problem. The key idea to solve such problems is to consider edges that connect them and start with vertices that have lower degrees. Since coupons have a price restriction L, items with lower prices have fewer options to choose a coupon. On the other hand, it's difficult to choose coupons for high-priced items. Therefore, we want to sort the price array P in ascending order and start with the item with the lowest price. Additionally, for each item, it's natural to use the coupon with the largest discount. This establishes a rational approach for buying all the items. Based on the previous idea, we have a plausible algorithm to solve the problem. To get straight to the point, this is the correct algorithm. I will explain later why the method achieves the minimum expense, but for now, let's go through the algorithm in detail. First, we sort P in ascending order and initialize a variable Q as an empty list and an integer variable ans as 0. Then, we iterate over the array P. For each item with price P, we search through the set of coupons L and D and add D to the Q if L is less than or equal to P. This way, the Q represents all the applicable coupons for the price P. We then select the minimal element from the Q, which indicates using that coupon for the target item. Finally, we add the discount price to the variable ans. Let's illustrate the algorithm with the example. First, we consider the item with a price of 3. Since there are no coupons available for it, the queue remains empty. We simply add 3 to ans and move on to the next item. For the item with a price of 6, we have 3 available coupons and add their discount prices to the queue. We then select the minimal value of 4 from the queue and use its coupon for the item with a price of 6. We also add 2 to ans. Next, we consider the item with a price of 11. Although we don't add new coupons to the queue, there are still 2 coupons in it. We prefer to use the coupon with a discount of 3, so we remove 3 from the queue. Now, let's think about the first item with a price of 13. It's worth mentioning that when we encounter 2 items with the same price, we should add coupons while considering the first item. Then, We move on to the second item with a price of 13. Finally, we've reached the item with a price of 15. After using a coupon for it and adding the discounted price to the variable ounce, we obtain the desired value, which represents the minimum expense required to buy all n items. This concludes the explanation of the algorithm. Let's analyze the total time complexity. First, we sort the array P in ascending order. Then, we insert a discount into the queue at most m times and retrieve the minimum value from the queue at most n times. If we use a priority queue for the queue instead of a simple list, the insertion and retrieval operations can be performed in logarithmic time. Therefore, the total time complexity is approximately 10 to the 7th, which is acceptable. As I mentioned earlier, I will prove the validity of the algorithm. How can such a pairing construction achieve the minimum expense for buying all the items? The main idea behind the proof is the concept of swapping coupons. As the example demonstrates, we can swap coupons if both coupons have price limits that are less than or equal to the lowest price of the two items involved. Moreover, swapping does not change the total expense. Therefore, we can prove that after multiple swaps, any purchasing method denoted by S that achieves the minimum cost will coincide with our algorithmic approach. We will prove this by induction on PI. First, let's consider the coupon we've used for P1 in our algorithm. Let C1 be the set of all coupons LD such that L is less than or equal to P1, and let C1' be the set of coupons used in construction S. L1 D1 represents the coupon for P1 in our algorithm, and as the algorithm demonstrates, D1 is the largest discount among the coupons in C1. L1' and D1' denote the coupon with the largest discount in C1'. It is crucial to differentiate between L1 and D1 and L1' and D1'. While L1 and D1 is used for P1 in our algorithm, L1' and D1' may not necessarily be used for P1 in construction S. The relationship between these notations is illustrated in the left diagram. We can now prove that D1' equals D1. If D1' were greater than D1, it would contradict the minimality of S, implying that swapping L1 and D1 and L1' and D1' would lead to a lower total expense. Likewise, if D1' were less than D1, it would contradict the maximality of D1. Therefore, we conclude that D1' equals D1. Now, by swapping L1 and D1 and L1' and D1' in S, we use L1 and D1 in the construction S while excluding L1' and D1'. However, the total expense remains unchanged since D1' equals D1. Finally, by swapping L1 and D1 with a coupon for P1 in S, we obtain the same coupon for P1 as in our algorithm. With slight modifications, we can apply the same approach to changing the coupon for Pi in S to that of our algorithm. Ci and Ci' are like C1 and C1' respectively, but remove coupons from L1 and D1 to Li-1 and Di-1. I'll skip the details, but let's follow this reasoning for better understanding. In conclusion, all the coupons in S can be transformed into those used in our algorithm. Hence, we can state that any construction S is equivalent to our algorithmic approach. This concludes the video. If you have any questions regarding the problem or any requests to solve other ABC problems, please feel free to comment. Thank you for watching the video.